Hi, welcome back to section 8.2. In the last video, we defined power series. And so right now I've got my power series, which I'm now going to call f of x. And so it's a function of x where you plug in x into this value right here in the power series. So a couple results about power series. Say if f of x and g of x are power series, then so are f of x plus g of x. So in that case, you would sort of get the coefficients by just adding each coefficients. So let's say we can add coefficients together. You can multiply power series and still get another power series. And the way that you get those coefficients is a little bit more complicated. If you think about when you multiply polynomials, you sort of have to add together all these different things that you multiplied together. And this is actually called a Cauchy product. And I'll refer you to page 429. And then you can also divide as long as your denominator is not going to be 0. Although the coefficients are complicated. Now, if you have positive radii of convergence for f and g, then you'll also have positive radii of convergence for the sum and the product and the quotient. And what it is sort of depends on things. But again, that's sort of getting into the theory of power series, which we are not going to concern ourselves with so much right now. But another theorem, another property of power series that is going to be extremely helpful to us in studying differential equation is about how you can take derivatives and integrals of power series. So here's our theorem. If our series f of x equals same old power series, and if it has a positive radius of convergence, rho, then f, the function, is differentiable for any x in the radius of convergence. And we can take the derivative termwise. So that makes sense. It makes sense that it's differentiable. I mean, it takes a little bit of effort to prove, which we're not going to do. But this is just a polynomial, right? And so if it's a polynomial, then you can take its derivative. And it makes sense that we would be able to take its derivative just by taking the derivative in the normal way. So the first term, the n equals 0 term, goes away because it's constant. And so you get the sum from n equals 1 to infinity. Bring the n down, leave the an the same, x minus x naught to the n minus 1. And that's for any x in our radius of convergence. So similarly, you can take the integral and you can do that termwise. So we get the sum from n equals 0 to infinity an over n plus 1, x minus x naught to the n plus 1 plus a constant in our radius of convergence. So that's good, because now if we're working with differential equations and we're working with functions that have the form of a power series, then we can do all the integrating and the differentiating that we want to do, and in the sort of normal way that we're used to. So there are a couple examples in the book of using this theorem. I think they're just really straightforward, and I don't think I need to do them right here. Of course, you can always ask if you want to see it. But what I find really confusing about power series is the summation notation and the indices, because sometimes you have to switch things around a bunch and things get really confusing. So I want to write out an example where we are shifting things, our notation around, just to get everyone used to that a little bit. So this is example 5 on page 431. And we want to show that if this identity holds, so we have two power series, and they are both equal to 0, or their sum is equal to 0. We are starting off at different indices, and then we have sort of different things over here. So it makes it a little bit hard to compare them, because when you add polynomials together, you want to add their like terms, the terms that have the same power or the same order. But these don't sort of match up. So that's the thing that we're going to want to do. So anyway, we're going to show that if this identity holds, then the first couple terms are going to have to be 0. And we get a n equals negative b n minus 1 over n plus 1 for all the rest of them. Okay. So let's do this. So first, rewrite both series in terms of x to the k. Okay. So I'm going to do the first one. In green. So step 1, set step 1A, I guess, whatever. It's just like when it's a little bit like substitution or whatever, you're changing your variables that you have to do when you integrate sometimes. So we set k equals n minus 1. And then n equals k plus 1. And we can write n equals 1 to infinity of n a n minus 1 x to the n minus 1. So the reason that I knew to set k equal to n minus 1 is because I had this here and I wanted to change that into k. So that needs to go to k, and so that's why I decided on that way to change it. I don't care if what things look like in the coefficient or anywhere else, but I want that power to be k, and so that's the key thing here. So if I do my substitution, I'm not going to do the limits on the summation just yet, but I can turn n into k plus 1, and then n minus 1 is going to be equal to k, And then I have x to the n minus 1, which becomes x to the k. Now for my summation limits, it's just like when you do a use substitution and you change the limits of integration. So when n equals 1, k will equal n minus 1, which is 0, k equals 0. And when n equals infinity, k will equal infinity minus 1, which is infinity. Okay, so now my second one, now I'm going to set k equal to n plus 1 because I want this thing to be k. And then I get n equals k minus 1. And so I can get my sum, n equals 2 to infinity bn x to the n plus 1 is going to equal the sum. Bn will become bk minus 1, and x to the n plus 1 will become bk. Now when n equals 2, k equals 3. And when n equals infinity, k equals infinity plus 1, which is just infinity, okay? Okay, let's copy our identity and drag it down here. There we go. So this thing will become, so to the green box, we will have k equals 2 to infinity of k plus 1, ak x to the k, plus our yellow box, which is k equals 3 to infinity, bk minus 1, x to the k equals 0. Okay, let's write this as a single power series. And so for k equals 0, 1, and 2, you're only getting contributions from the first term. So when k equals 0, we'll get 1 times a0 x to the 0. So that one is k equals 0. For a k equals 2, we'll get, or k equals 1, excuse me, we'll get 2a1 x plus, so that one's k equals 1. K equals 2, we get 3a2x squared. K equals 1. Now the rest of them that should be k equals 2. And for the rest of them, now we can sum them all together. So for k equals 3 to infinity, we get the sum of this coefficient plus this coefficient, which is going to be k plus 1 ak plus bk minus 1 quantity times x to the k. And we have this equal to 0. And so from the theorem that we had last time, at the end of our last video, this implies that all the coefficients equal 0. So that gives us a0, a1, and a2 have to be 0, and k plus 1 ak plus bk minus 1 equals 0 for k greater than 3. And so we can rewrite this to look like what the problem asked us to write, where we'll solve for ak, and we get ak equals negative b to the k minus 1 over k plus 1. And we could change that k to an n and switch it back if we want to. It doesn't really matter one way or the other. But anyway, that's what we wanted to solve. Okay, so the last thing we're going to do is talk about what functions can be represented as power series, because that is sort of exactly the functions that we care about working with right now. And so we're going to have a definition. A function f is said to be analytic at x naught, at a particular point, if in an open interval around x naught, the function is a power series. The same power series that we always have, n equals 0 to infinity, a n x minus x naught. And we need this to converge for some positive radius of convergence that has a positive radius of convergence. So some examples of analytic functions are polynomials. Of course, polynomials can be represented as a power series because they basically just are a power series with most of the coefficients equal to 0. So polynomials, all the sort of normal functions, rational functions, as long as the denominator is not 0, trig functions, exponential, you know, all the usual suspects. Now, because of the theorem that we saw earlier in this video, where you can take the derivative of a power series and it's another power series, that means that you can take the derivative of an analytic function because you can represent it as power series. So we have the fact that if f is analytic at x naught, then derivatives of every order exist also at x naught. So if f is analytic, then you can take derivatives over as many times as you want, which is a really, really nice property of a function. And in fact, we know how to take those derivatives. So if we have f of x equals the sum n equals 0 to infinity a n x minus x naught to the n, then f prime of x is going to equal the sum from n equals 0 to infinity of n a n x minus x naught to the n minus 1. And similarly for f double prime, we can just take that n minus 1 down, n equals 0 to infinity n minus 1 a n x minus x naught to the n minus 2, and so forth. So if we take our jth derivative, x, we end up with some times n minus 1, n minus 2, yada, 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 to n minus j minus 1, a n x minus x naught to the n minus j. So let's plug in x naught and think about what the values of f, of all the derivatives of f are at x naught. So plug in x equals x naught, and we get that f of x naught the x equals x naught is going to kill off every x minus x naught term except for when that exponent equals 0. So for f of x naught, we just get a 0. F prime at x naught. Now we'll kill off everything except for when n equals 1. So then we get a1. F double prime, we're going to kill off everything except for when n equals 2. So then we get 2 times 1 times a2. Yada, yada, yada. Fj at x naught equals, now we're looking for when n equals j, and we'll get j times j minus 1 times j minus 2 times j minus 1 is just 1 times aj, which of course is equal to j factorial aj. Okay, so that's pretty interesting because now we can solve for the coefficients of our original f. So remember our function f of x equals n equals 0 to infinity of a n x minus x naught to the n. But all of our a_n's we can sort of see from up here equal, if we divide off by that sort of j factorial or n factorial, whichever one the index doesn't matter, this is going to equal in sum from n equals 0 to infinity, an equals f nth derivative evaluated at x naught over n factorial times x minus x naught to the n. This is our Taylor series. And so we have essentially two different representations. We have of f, and we have our sort of generic power series version, and then we have our Taylor series version. And because we could subtract those and it would be equal to 0, and then all the coefficients an minus this guy would equal 0. So if two power series are equal for all x, or for all x in an interval, then their coefficients are going to have to be equal. So the key thing here is that any power series that converges in a neighborhood of x naught must actually be the Taylor series of whatever function that you converge to. So the point here is that if you know that you have a function that can be represented as a power series, that power series is the Taylor series. So you actually even know how to compute it. So that's going to be really useful when we start using this to solve differential equations. And so we'll see that in the upcoming sections.